Among us, Sir Michael Atiyah, very well known of all mathematicians. As you certainly know, he was a field medals, and also he received the Nobel Prize. And he will talk to us from quantum physics to number theory, geometry explores the universe. Please.
Thank you. As you probably know, over the last 30 years or more, there has been great interaction between mathematics and physics, and a large part of the mathematics is of a geometrical kind. This interaction has been very exciting and has had enormous benefits, both for mathematics and for physics. A lot of surprising results have come into mathematics from physics, which apparently had no relation to physics. And physicists have learned to use a lot more advanced mathematical ideas, which in the past were also very far from physics. So it's been very beneficial for both sides, this interaction. I was involved with it for many years, first rather actively, now a little bit more from a distance. I'm retired. I've been retired for 13 years. So, but I'm still interested in the relation between mathematics and physics. And I was going to talk here about my views. I don't have theorems or results or anything spectacular to say, but I am interested in the relationship and from the point of view of a mathematician. And I'll try to explain what I mean by that. Physicists are very good, they know the physics. I can't add to the physics, but I can add something coming from the point of view of a mathematician. Now the title is, you see, very all-embracing. Quantum physics, number theory, and the universe. Everything is included. In the universe, I mean not just the physical universe, but also the universe of ideas. So it includes all mathematics. So it's a big topic. So now, I'm going to start with a lot of quotations by famous people who describe their view about mathematics and physics, and in particular, the importance of beauty in mathematics and physics. And this is something that I feel very strongly myself. And I feel that if there is an ultimate theory of the universe, a physical theory, it should be beautiful. Whoever created the universe, God or nature, then we believe certainly that it's built on good, sound, logical, mathematical foundations. And, you know, it's a beautiful world, so there should be a beautiful theory. The mathematics of it should be extremely beautiful. Also, it should be, in some sense, unique. There should be, only one choice that God could make to make this world. He shouldn't have had to choose lots and lots of different ones, and he shouldn't have to fiddle the equations to get the right answer. It should be, God-given. It should be one theory. So that's the kind of view that drives an individual to look for a theory. Some physicists are more pragmatic. They look at experiments and results, try to make the results fit the theory, fit the experiments. I prefer to look for above and to look for a theory which is really beautiful and unique and coherent. Of course, we're a long way from that, but that's my sort of point of view. So let me start now by telling you some of these quotations. Now, the person whose quotations I like the best is in fact Albert Einstein, because he was a very famous man in his time, and so people asked him many times what he thought. So he had many quotations. So here's the first one. He quotes very often about God. It's not quite clear which kind of God Einstein believed in. Whatever he was certainly a physicist and a mathematician. I want to know how God created the world. I'm not interested in this or that phenomenon, this spectrum, or this or that element. I want to know his thoughts. The rest are details. Second one, about quantum mechanics. He had very strong views about quantum mechanics, and he had many arguments with Niels Bohr about quantum mechanics. What he says here is that quantum mechanics deserves much respect, but an inner voice tells me that it is not yet the real thing. The theory gives much, but hardly brings us to the mystery of the old fellow. He's on speaking terms with God, you see. At any rate, I am convinced that the old fellow does not throw dice. He didn't believe in the sort of randomness of quantum events. And then his next quotation is, the law is clever, but not malicious. In other words, the word is used is subtle. The word is subtle, but not malicious. He doesn't mislead us. We aren't tricked by some dirty trick. And if God created the world, it was clearly not his main concern to make it such that we understand it. That's a sort of he spent a lot of his time trying to understand it. Obviously thought God had set a hard problem. So that's the first collection. Now, then the next one is really a nice philosophical one. The most incomprehensible thing about the world is that it is comprehensible. And you see, this is a very deep statement, because what it's saying is that we scientists, mathematicians, physicists, we believe that the universe is built on fundamental mathematical equations of some simplicity. Maxwell's equations, Einstein's equations, and so on. Now, why do we believe this? Why should it be true? It's an act of faith on our part. Just like some people believe in God as an act of faith, well, we mathematicians believe that the universe is built on mathematical principles. Why? Well, it's a matter of, we don't know. But so far, the evidence is in our favor. We've made a lot of success by assuming that there are mathematical equations that govern things, and so on, we go on believing in it. But nevertheless, it is really rather remarkable. Einstein says it's not clear why we should be able to understand the world. And the second one is a more personal one. It is, don't worry about your difficulties in mathematics. I can assure you mine are greater. He was, of course, a physicist, not a mathematician. Even in his great work on relativity theory, he had to get the help of mathematicians. But he had great physical insight, which enabled him to see through to the answers. Now some more quotations from a variety of mathematicians. First here is Pythagoras, very old one. Numbers rule the universe. Where are we? Lost this one here. Numbers rule the universe. So these are people who think that mathematics is outside in the world. Plato, God is a geometer. Isaac Newton, God created everything by numbers. James Jeans, the great architect of the universe, now begins to appear as a pure mathematician. And Bertrand Russell says mathematics possesses not only truth, but also supreme beauty. So these are all people who think that mathematics is there in the universe. Now Hardy was a pure mathematician and a very eccentric mathematician with strong views, and here is his view about the role of beauty in mathematics. The mathematicians' patterns are like those of the painter or the poets. They must be beautiful. The ideas, like the colours or the words, must fit together in a harmonious way. Beauty is the first test, and there is no permanent place in the world for ugly mathematics. By which he meant, perhaps the first time you discover something, you discover it by some very bad method. But if it's important enough, you will think and improve the method until the result becomes clear and beautiful. So beauty is to be aimed at, even if in the first instance you don't get it. This is a surprising quotation. If you look at the bottom, you'll see who it's by. Winston Churchill, not a famous mathematician. I had a feeling once about mathematics that I saw it all. Depth upon depth was revealed to me, a quantity passing through infinity and changing its sign from plus to minus. I saw exactly why it happened. But as it was after dinner, I let it go. So he's a mathematician manqué. He didn't become a mathematician. I was surprised at this quotation, but I found it somewhere in a book. It might be a spoof. I don't know. I can't guarantee that Winston Churchill said this, but it's too good not to use. And now Hermann Weyl, one of my favorite mathematicians, and this famous remark of his, says, my work always tried to unite the true with the beautiful. But when I had to choose one or the other, I usually chose the beautiful. Now, this seems a very perverse remark for a mathematician to make, because surely mathematics is about discovering the truth, producing proofs. Proof is the ultimate check in mathematics, and if you have to choose between a beautiful theorem and something which is obviously true but not beautiful, why should you choose the beautiful one? Well, it's a deep statement, really, but I think you can understand it in the following way, that the truth, you never actually know whether you've got the truth. You search for the truth. What you have at any given moment is some step towards the truth. It may be a mistake. Maybe you're not seeing correctly. So you'll never know whether you've got the truth. That's eventually you aim towards the truth. Beauty, on the other hand, you immediately recognize. If I say something is beautiful, you can't argue with me. It's my personal opinion. So beauty is something the individual feels subjectively, and he knows he's right because it's his taste. And beauty is what guides the mathematician in his own work. He looks for beautiful things, and that's how he goes. He may aim for truth. Eventually, far in the future, he's aiming for truth. But the way he gets there, the light that shines the route for him, is beauty. So I think that's what Hermann Weyl meant. Now, I'm now going to quote from famous physicist Paul Dirac, and these are quite long quotations. Hope I can read them from here. I'll read it with you. So this is about mathematics. It's taken from a lecture he gave in 1939 about mathematics and physics. And the lecture itself is an excellent lecture. And I read it again. And his predictions about the future of physics have turned out to be remarkably accurate, and their relation with mathematics. He had deep insight. This is 1939. It's a long time ago now. Pure mathematics and physics are becoming ever more closely connected. That was then. I say now, but history is much further back. Though their methods remain different. One may describe the situation by saying that the mathematician plays a game in which he himself invents the rules, while the physicist plays a game in which the rules are provided by nature. But as time goes on, it becomes increasingly evident that the rules which the mathematician finds interesting are the same as those which nature has chosen. It is difficult to predict what the results of all this will be. Possibly the two subjects will ultimately unify, every branch of pure mathematics then having its physical application. Its importance in physics being proportional to its interest in mathematics. And this quotation goes on. At present, we are, of course, very far from this stage, even with regard to some of the most elementary questions. For example, listen to this. Only four-dimensional space is of importance to physics, while spaces of other numbers of dimensions are of about equal interest in mathematics. It may well be, however, that this discrepancy is due to the incompleteness of present-day knowledge, and that future developments will show four-dimensional space to be of far greater mathematical interest than all the others. Now, that's a remarkable prophecy. As some of you know, in the last 20, 30 years, remarkable facts have been discovered about four-dimensional space which are quite unique and not true of other dimensions. This is one of the most remarkable discoveries of the last part of the 20th century. And here is Dirac forecasting it in some sense, allowing for it as a possibility. He's a very, very deep thinker in Dirac. And then one more quotation from Dirac. So he's looking to the future. I would suggest, as a more hopeful idea for getting an improved quantum theory, that one takes as basis the theory of functions of a complex variable. This branch of mathematics is of exceptional beauty, and further, the group of transformations in the complex plane is the same as the Lorentz group governing the space-time of restricted relativity. One is thus led to suspect the existence of some deep-lying connection between the theory of functions of a complex variable and the space-time of restricted relativity, the working out of which will be a difficult task for the future. Well, that is a remarkably accurate prediction of what has lot of what has happened in physics in the last 20 years. The use of complex variable methods inside present-day physics string theory is widespread. There is also the work of Roger Penrose, which is tangential but part of the same story. So complex variable theory has become a very, very important part of modern theoretical physics, and part of the reason is, as Dirac points out, its connection with the Lorentz group. So it's a very, very far-sighted statement, so one has to take seriously the views of physicists of this caliber when they look to the future. His contemporaries wouldn't have agreed. He was thought of as an old man by this time, making, crazy remarks. But his remarks have turned out to have much longer life than some of his contemporaries' own views. Now, I want to turn to this topic here. I've headed it Number Theory, Geometry and Physics. There's number theory coming in the first time in my talk. I've put down three famous names of pictures here. On the left-hand side is Alan Kohn, who developed a beautiful theory of non-commutative algebra, who was great interest in physics, and he ended number theory. Roger Penrose, I mentioned in the middle, he was a fellow student of mine when I was a student in Oxford, in Cambridge, and eventually a colleague when we were both professors in Oxford, and I've worked with him quite closely. And the last is Edward Witten, who is the leading theoretical physicist of our time, and whom I've known since he was a young man. I still think of him as a young man, but he's over 50 now, but for some people that's still young. Now, I put them up there because they represent three schools of thought about how to develop physics. And I wrote a lot about this at a conference held to celebrate Roger Penrose's 65th birthday, I think. And if you allow me, I'll read this extract because it's very much what I think about this story. So as I say here, as we all know, the fundamental problem that all physicists would like to solve is how to reconcile quantum theory with general relativity. In other words, how to produce a unified theory incorporating quantum gravity. There are many different approaches to this goal, and it's not, I hope, blasphemous to make comparisons with the way rival religions offer alternative approaches to God. To the protagonists, the various religions are mutually incompatible and at times distinctly hostile. To the skeptic, the different religious approaches simply cancel each other out, leaving a vacuum. At the other extreme, we have mystics who see underlying commonality in all religious experience and search for some fusion. And as a side remark, we mathematicians might note by analogy that a combination of oscillatory functions can cancel themselves out, but yet leave a few delta functions at specific frequencies. If we turn now to the different approaches to quantum gravity, there are several rival philosophies or religions. The orthodox one is string theory, associated with quantum field theory, and here the prophet is Edward Witten. We then have the twisted approach, led by Roger Penrose, and there's finally a newer approach, newer at the time, based on non-commutative geometry, pioneered by Alan Kohn. Now, as skeptics, we have the hard-headed experimentalists who have little time for theories which deal with monstrously small or large quantities, beyond the realm of measurement. On the other hand, there are mystics, among whom I include myself, who hope for a synthesis which embraces all of the rival theories. As a mathematician, I would find it a pity if God had not found some use for all the beautiful ideas that have been put forward. So that's my view. I'm a mystic. And I have to say that was written about in 1996, and the developments since that time have given some evidence in my favor. Links have been found between the works of all three of these people, and the links are getting stronger as we go along. So some tendency towards fusion is actually taking place. Now, I want to come down. That was my list of quotations, and I hope you enjoyed the quotations. They're very important because they show you how people think. I classify myself as a follower of Einstein and Dirac. I believe the same things that they believed in, the importance of beauty, the aim for simplicity, aim for a fundamental theory we can understand, and I share that view with Einstein and with Dirac. And towards the end of his life, Einstein was pursuing this unified theory he thought should exist. Everybody else thought he was wasting his time. He was an old man. Why didn't he get down to do some decent work? And here he was speculating about this unified theory, which he never, of course, succeeded in doing. But really, he was far ahead of his time. Developments after Einstein's life have, in fact, shown that the things he was searching for are actually now being produced. Physicists are unifying theories in the way that Einstein really wanted. So Einstein was really right. And when people, if they criticize me, saying an old man doing the same thing, I say, well, if I'm in the same class as Einstein, I'm quite happy to be criticized. It's a good gang to belong to, Einstein and Dirac. And now, I'm going to make a few suggestions about mathematics and physics, and which will are some principles which might help to guide us to the right theory. The technical details are not important. The technical details the literature is full of technical details. I want to keep out of that. But I wanted to talk about the following things. As you know, there are the real numbers and the complex numbers are the fields we learn in mathematics and we love and have enormous use for them. Of course, it took many hundreds of years to develop first the real numbers, and then many more hundred years to get the complex numbers. And then in the 19th century, William Hamilton came up with the idea of Quaternions, which are beyond complex numbers. I remind you, Hamilton was a mathematical physicist of great stature in the early part of the 19th century. And when what he was trying to do, he realized how important complex variables was for two-dimensional physics. And he wanted to find a similar branch of algebra which would deal with three-dimensional physics. And he tried and tried and tried, and he didn't succeed. And finally, one day, he discovered that he should be looking at four-dimensional physics. With four dimensions, you have the Quaternions. And this was a great day in his life, and he realized it, and he spent the rest of his life mainly developing the theory of Quaternions and applying it to physics as it was at the time. And again, people thought he was wasting his time. Books have been written about what they call the Irish tragedy. Hamilton, the great mathematical physicist, wasting his time on a little bit of algebra. But again, history has shown that he was right, because Quaternions, as you know, are, unlike the complex numbers, are non-commutative. The multiplication of Quaternions is not commutative. And this is the first time non-commutative things entered into mathematics, and of course later on they entered into quantum mechanics, and Kahn has developed the theory much further. So non-commutative ideas begin with Hamilton and the Quaternions, and moreover, more than that, the unique Quaternions is the group commonly called SU2, 2 by 2 unitary matrices of determinant 1, which is the first group that physicists use where they're studying what are called gauge theories, trying to explain the forces of nature. So both in the general spirit of non-commutative algebra, but even more in the technical details of what he developed with Quaternions, these have turned out to be absolutely fundamental 100 years after his death. He even wrote down a nice formula which essentially means that he rediscovered the Dirac operator, the Dirac equation, 100 years more before Dirac. So he was, again, very far ahead of his time. Now, after the Quaternions, people tried to see, well, could they find other algebras beyond the Quaternions? And with a lot of effort, they found something. They found what are called octonions. When I was a student, they were called the Cayley numbers. But there's a lot of dispute about who discovered what. So the octonion is a nice neutral word. The word octonion indicates that it's 8-dimensional. The Quaternions are 4-dimensional. Complex numbers are 2-dimensional. The reals are 1-dimensional. This is an algebra which is defined on 8-dimensional space. And it's an algebra which has a multiplication, but the multiplication is not only not commutative, it's not even associative. You know, otherwise A times B times C is different depending on how you bracket them. So it's a very bad algebra from the point of view of algebraists. Nevertheless, it has one important property it shares with all others, is what's called the division algebra. Every element that is not zero has an inverse. And the division algebras stop here. There are no more division algebras beyond this point. Even if you weaken the hypotheses and require much less than is present here, these are called norm division algebras. Even if you weaken it in a topological context, it's finally proved the big theorem in topology, there is nothing like these beyond dimension 8. And corresponding to these algebras, there are corresponding geometries. In particular, there is the predictive plane. Over the real numbers, the complex numbers, and the Quaternions, you can define a predictive space of any dimension, 1, 2, 3, 4, and so on. Over the octonions, you can only define the predictive plane, the predictive line, and the predictive plane, and you cannot define a predictive space of dimensions 3 or more, for very fundamental reasons, because it's known that if you could do, then the algebra would have to be associative. So you have these 4 division algebras, which sort of get, the first 2 are very nice, they're fields, and then the Quaternions are non-commutative, but still you can do a lot with them, but you have to distinguish between left and right actions. The octonions seem to be much worse. They are a division algebra, and they end this list, but they don't form an associative algebra, so you might say they're not very nice. In fact, Dirac made a quotation in the same lecture I mentioned before. He said that Jordan, the physicist whose name is now associated with Jordan algebras, one of the early pioneers in quantum theory, he was trying to develop a kind of algebra for physics, and he invented Jordan algebra, and he liked the octonion multiplication. And Dirac says this was obviously, this theory never got anywhere. It was obviously a mistake because the octonions are so ugly. I mean, the multiplication is not associative. Non-associative algebras are not very beautiful. And that was one case. where Dirac made a mistake. I'll try to explain. There is some beauty here, but you have to look hard to find it. And I'll try to explain where you get it from. Anyway, I want to say that the four division algebras are really very important, and the last one is in some sense the most important. You might think it was the worst, but in some sense it's like Cinderella, the poorest one, but it's the best. Now, this is explained by a rather beautiful object called the magic square, which goes back to Jack Tietz and Freudenthal a long time ago, and it deals, you can write it in many different forms, but I'll explain it here. So it's a 4x4 square. Along the top, these are the isometry groups, actually, of the projective planes. The SO3 acts on the real projective plane, this acts on the complex projective plane, preserving not only the complex structure but the metric. This acts on the Quaternion projective plane, and now here the Octonian plane has a symmetry group just like the others. This symmetry group is an exceptional Lie group. As you know, there are the Lie groups, simple Lie groups, come in the three classical families: real, complex, and symplectic, or the real numbers, complex numbers, and Quaternions. And then there are 5 exceptional groups. The first exceptional group is not on this list, it's called G2. That actually is the group of automorphisms of the field of the division algebra of the Octonions. And then down here we have F4, the next one, and then we have the next 3, E6, E7, and E8. So the classical groups appear this part of the story, this part the exceptional groups. This matrix is symmetrical, you notice? So they appear here and they appear there. And what it's supposed to be describing is you take the algebras, the division algebra I call systematically AI, I going from 1 to 4 or 0 to 3, and then you take the tensor product of the two of them. It's not an algebra anymore, but so you think of a pair, and then you can define not only this row, but another row, and another row, and another row. And if this row is the projective planes, this one is actually the complexifications of that planes. This one is the quaternionification of that one. And this one is a bit of a mouthful, it's the octonionification of that one. You have to make sense of those terms, but roughly speaking, that's how it goes. So this square has you can go out along the rows and you can go down along the columns, it's symmetrical, but the important thing is that the classical groups appear here and the exceptional groups appear there, and they belong to the Octonions. If we didn't have the Octonions, we wouldn't have the exceptional groups. Well, you might say that would be no great loss if you haven't met the exceptional groups, but if you look at them carefully, they're very beautiful. For example, the exceptional group E8 is closely related to the icosahedron, and even if you haven't met E8, you'll surely know about the icosahedron. And E7, these are also related to regular solids. So these are very important things in the whole of mathematics. They turn up in many places. So the exceptional groups are important, and the Octonions, which give rise to them, are important. So this square, and you can write down the groups, you can write down the projective planes. For example, if you write down the projective planes, then you notice that they have dimension 2, 4, 8, 16. Those are the real dimensions of those planes. That when you complexify them, they double again. So then they become now 4, 8, 16, 32. And again, when you go down here, you double again. So this last one is dimension 128. And every projective plane in every space of the in this picture has twice the dimension if you go that way or this way. So it's a very remarkable sort of story with these magic squares. Many people get very excited by it, mathematicians. Now, I want to make a proposal, which is not entirely new, but it's if you look in the literature, you will find a lot of people who say vaguely things like this, but I want to say it with a bit more emphasis. So the 4 division algebras, I would like to suggest, correspond to the 4 fundamental forces of nature. The 4 fundamental forces of nature, if you read the popular literature, you should know by now, they are the electromagnetic force, the weak force, the strong force. These are the forces involved in the structure of the nucleus of nuclear material. And then finally we have gravity, which is, of course, large-scale gravitational attraction and cosmology. These are the 4 forces. These first 3 are the ones which are nowadays well understood in quantum mechanics. There is a unified theory of these first 3, which is called the Standard Model. Gravity doesn't fit, and people have been trying for the last 20 or 30 years to bring gravity into the same framework as these 3 and unite it. That's the search, which is not yet completed. A lot of work's got into it, a lot of results have been found, but the search still goes on. Now, I mentioned here Dirac's mistake. I think he was wrong to think that the Octonians were ugly, so he allowed one mistake, he made so many things right. And now, so this proposal I suggest is work in progress. I'm thinking about it, other people are thinking about it. So the key idea is that gravity corresponds to the Octonians. These correspond to the classical fields, real, complex, and Quaternions. This one corresponds to the Octonians. Because the Octonians are much harder, gravity is much harder, but because the Octonians are also very beautiful, looked at the right way, gravity should also be very beautiful too. So the real theory, which we would like to get to, which may not get to in my time, may get to in the time of some of the younger people here, perhaps some of the younger people here will contribute to the theory, should I aim to include gravity with all these theories in such a way that gravity is seen to be very much consequence of the Octonians and the exceptional groups. This would be a really beautiful end to the search. But it ends here because we know that the Octonians are the last division algebra. There is nothing beyond. You see, if you start only with thinking about Lie groups, there are lots of Lie groups of any size, matrices of any size. And when physicists start to play around with them, they experiment with different models, but they don't quite know where to stop and why. If you focus on the algebras, which only end up this fourth one, you must stop there because nothing exists beyond that point. So to give the kind of finality to your search, it may be wrong, maybe I'm not on the right track, but if I'm right, then this is where we should look for the final theory of gravity. It'll be hard because we know the Octonians are hard, but when you find it, it should be a beautiful theory and it should be unique because there's no other choice. The Octonians are the only thing of division algebra of that kind. So we should get a theory which is beautiful, unique, and final. That's the message of this proposal. I mean, the proposal is a vague philosophical one, and many people have thought along similar lines, but I want to emphasize the uniqueness and the finality of an approach based on this idea. Now, let me say a little bit about two interesting things in mathematics, zero and infinity. People always have had troubles with infinity. If you go back to Achilles and the tortoise, and you go back to the analysis in the 18th and 19th century, dealing with infinity was the great challenge of mathematics. How do you understand the calculus, infinitesimals? How do you pose limits? This was a very difficult problem, and mathematicians finally succeeded in what's called taming infinity, keeping it under control, making it rigorous, so you can talk about infinity, talk about tending to infinity, and mathematicians think they understand infinity. Zero, you think is much easier, but of course 1 over 0 is infinity, so they come in pairs, so to speak. And the infinitely small and the infinitely big are the opposite ends of some kind of spectrum. So you shouldn't think of 0 as trivial. 0 is equally difficult in a way. For example, if you think of the space, is it infinitely divisible? Can you go on finding smaller and smaller points in space of 0 dimensions? The Greeks defined a point as something which has position and no size. But is there such a thing? Are there things with no size? Is there a point which is 0 magnitude? So there's difficult physical notions, and mathematics has to reflect those in a way. So don't think of 0 as being trivial. Now, at the same time as after the discussions about infinity in the 19th century, in the 20th century, there was a lot of discussion about the foundations of mathematics. And the famous names here are those of Hilbert with his program for formalizing mathematics. There was Kurt Gödel who came along and showed that it was impossible to have a system of the kind Hilbert wanted. There was Brouwer, who started his life as a topologist, proved a famous fixed point theorem, and in later life he became a renegade. He refused to believe in his theorem because he said the proof was only an existence theorem, it didn't show you how to construct it. And he led the view, what became called constructivists, that the only things that you can deal with in mathematics are those which you can actually construct, at least in principle. Something which there was an algorithm. And he didn't believe in existence theorems which showed something existed without any indication how you actually construct it. Now that was a big debate between the constructivists and the formalists. And one of the things, when I was studying a student, these were all battles of the past. You know, they'd been fought and won or lost, and we didn't care much about them. We just worked on our mathematics. But I was always rather struck by the fact that Hermann Weyl, who was the mathematician whom I most identify with in terms of he did so many things in mathematics, so many beautiful things, and in physics, that I was very surprised that Weyl, although he'd been a protege of Hilbert, at the end of his life, or toward the end of his life, he said, I really have to believe that Brouwer is right. I really think that we should be honest with ourselves and say things which we cannot construct don't have the same real existence as things you get by existence theorem. So he became at least philosophically, if not in practice, a constructivist. And I was very surprised at that. I thought he was, and Hilbert was horrified because Weyl was his pupil, his protege, and here he was going over to the side of the enemy. And the terrible sort of tragedy. But in a way I've come around now, as I'm getting older, to believe that something in what Weyl said. You see, constructivists are of course closely related to computation. If you can construct an algorithm which you can feed into the computer, which will after some amount of time give you an answer, you have computed something. But most real numbers, for example, can never be computed. You can't find the typical real number. If by definition you can find it, it's not typical. It's one of these catch-22 situations. So the constructivists had a point. We never actually deal with numbers that aren't constructible. We deal with theoretical notions about real numbers, but then the real numbers that we use and hold in our hand are things we can construct. Now this becomes important when you look at the link between mathematics and physics, because in the world of physics, things should never be infinite, nor should they be infinitely small. Infinite number may be something mathematicians can contemplate, going to infinity, but in the physical world, things really have to remain finite. And similarly, not only finitely big in size, but finitely small. You can't go down to infinitely small things. And most physicists understand this. For example, they will say that the nature of space is that at very small scales, space may not be continuum. Maybe there's some smallest size, because what does it mean to have a continuum? We can't actually test anything by any physical experiment, whatever, if it's so small that nothing like light or anything can get inside it. So there's a limit to what experimental physicists can actually see. And beyond that limit, it makes no sense to a physicist to imagine there is a continuum. So you might think that you should really have some kind of granular structure of matter at that stage. And this is actually been raised by physicists. Is space-time granular at very small scales? And in many ways physicists believe this, but they don't necessarily follow that up in practice. It's too difficult to believe. But here is the quotation from the well-known textbook by Bjorken and Drell, volume 2, which deals with quantum field theory, called Relativistic Quantum Fields. And here is what they say, a long passage, I've quoted a little piece of it. Even if there is a granularity at small distances, if we are to retain microcausality, the influence of one granule upon the next must be retarded. Think of shuffling pebbles on the beach. Each one knocks the next one, but there's a little time lag for it to get across to the other side. So what they're saying is that if space-time isn't continuous at the lowest limit, then you should allow yourself to have retardation in signal propagation. And in mathematical terms, that really means that you should study differential equations with a retardation in them. So this is my next slide. A retarded differential equation, here is the simplest one you can think of, a function of one variable, derivative f of x, plus some constant, and here you have x minus another constant r times minus time. Let's see, I think I got mixed up with basic time. I think I don't really want time. I've got a few too many variables in here, never mind. Basically, the important point is that this is, value here is not x, but x minus r. It's shifted away. Forget that t, it's a mistake. So you have x here, but instead of having the value of the function at the same point, the value of the function is a previous point. In other words, there is an influence of the past on the present. And this is then called the retarded equation. And these things occur in electrical engineering when they called delays, and you have feedbacks and so on. So they're very important. Signals can propagate with a delay in the world of engineers, and it might propagate with a delay in the world of fundamental physics. And such an equation, this example, it trivially can be solved like a hyperbolic equation, if you just know the situation in the past, you can go step by step over intervals and keep repeating integration and solve this function going forwards one way in time, and you can go backwards in time so long as you can differentiate any number of times. So, and if you notice that one of the features about this retarded equation is that although it's a first order equation, the initial data to solve it is not just the value at a point, but the value over an interval. You need to know the value of the whole interval, and then you can propagate it by steps. So you see a bit of a similarity to quantum mechanics here. The state that determines the initial state of the system is not a function number, but it's a function on an interval, Hilbert space. So once you start dealing with retarded differential equations, you're in a very different game from ordinary differential equations. Of course, you can do this with many variables, and you can imagine redoing physics with retarded equations inside. And if you believe that the fundamentals of physics do require retardation at the fundamental level, then you should take this seriously. So now the difficulty is that how will you do it? It's going to be, how will you combine this notion of retardation with all the beautiful structures that physicists like to use, like Lorentz invariance and so on? But before that, you have to worry about another factor. This is an equation which is shifted backwards here, retarded. Here you take two terms. This is going one sign, this is a different sign. So this is an equation where the derivative depends not only on the past, but on the future. Well, that's a bit of a difficult notion, but if you forget about it, if you think that these are very, very small distances, at very, very small scales, we don't know about scales, and we don't know about time, small time scales, so we only have to worry about this question of very, very small scales. But nevertheless, you may have to worry about equations like this, which are called mixed equations or shifted equations, both forward and backwards. Now, one question you can ask is, how can you make the notion of a retarded differential equation in Minkowski space, where there is no distinguished time direction? What does it mean to delay when you don't have a fixed time? Well, you might think it's impossible, but that's not true. You see, you observe the following, elementary mathematical fact. I keep getting mixed up with t and x here, forget about that. T is x here, it isn't there. Anyway, the point about it is that, or t, if you take a translation by a certain amount on a line, that is a group element. You should translate by jumps. But the infinitesimal generator of that is differentiation. That's the derivative. The derivative is said to be the Lie algebra, and this is the Lie group. So you could formally think of translation as the exponential of the derivative. This is an operator which has the effect of shifting x by r. And these equations, if you have a mixed equation, then I say it's a bit like elliptic equation. You need conditions at both ends, but forget that for the moment. Focus on this statement here, that you could try to make sense of translation by writing it formally as the exponential of the derivative. Now, this was taken up by Greg Moore and myself in a paper, which I suppose it's on the web, it's not actually published yet. And so we speculate on the role of relativistic versions of delayed differential equations. And the relativistic invariance implies we must consider both forward and backwards, and so on and so forth. But the key point is that in order to define retardation in Minkowski space, what you need is a first order operator, like d by dt, which is invariant in Lorentz space. Now there's only one first order differential operator which is invariant under the Lorentz group, and that was discovered by Dirac. It is called the Dirac operator. And the reason he discovered it is he wanted precisely a first order differential operator invariant under the Lorentz group, so you can write down relativistic versions of the equations of quantum theory. So this is just using Dirac's idea. Now the only thing you have to notice is that the Dirac operator acts not on scalar functions, but he had to invent spinors. Spinors are the things on which the Dirac operator acts. Once you've allowed spinors to act, then the Dirac operator is a relativistically invariant operator in Minkowski space. It can even be defined on a curved background, so it's a very universally defined operator. And now if you consider this operator here, this is the ordinary Dirac operator, and I've added to it, so this would be like the derivative term, I've added to it here the bit that's the translation term, some multiple, and I have an exponential of minus r times d. This operator is meant to be the relativistic version of the one-dimensional operator I wrote down before, which includes the shift or translation in time. And we did some sort of arguments based on this to get some evidence of what these numbers r should be. First of all, we found the number r should be quantized in some units, and the scale should be approximately a constant wavelength of some particle, and the smallest particle, if you took it to be the neutrino, would give you a scale like this. On the number k, we found we had some relation to Einstein's equations, and so it related to the cosmological constant, and so we got a scale for this number k, or rather its ratio to the Planck's constant, 10 to the minus 56. Well, this cosmological constant is one of the mysteries of cosmology, why it's so small and why it's there. And in this little model, we meet both nuclear physics at this level and we meet cosmology at that level, just from the idea of using this operator. Now, this is a very rudimentary fact. We haven't yet pursued this in any depth. We don't quite know what you can do with it. But it does make sense as an operator. If you ask what this means, what it means is the following, is that any wave function, this is a linear operator, although it doesn't look linear, it's a linear operator, and if you take any wave, you can decompose it into plane waves, each propagating in a particular direction, and then, so you take that Fourier component of the wave, and then you retard that in the direction of its own time. So when you've done that, you integrate back again, and get back the final function. That is the result of this operator. So it retards each Fourier component in its own time. It's a perfectly good sense, and it's an intrinsic Lorentz invariant notion, and it can only be done because you have this Dirac operator is Lorentz invariant. So there's no other solution to this problem. If you want to introduce retardation into conventional Lorentz invariant physics, this is the only choice. There is nothing else you can do, because Dirac discovered this was the only operator you could use. So I like things that are unique, because that is the only solution to a basic question. You ask a question, there's one and only one thing you can do, and that's it. It may not be the right question you asked, but if you ask that question, you get one and only one answer. So that's I think, worth at least investigation. This is a very recent paper, it's not yet published, it's on the web, but at least it indicates ideas. Now, let me go back to my magic square, with slightly different form. I said there are four fundamental forces, the three forces, the electromagnetic force, the weak force, the strong force, and then there is gravity, the fourth force. But number four comes in another way too. We live in four-dimensional space-time. Most of the time we think we do anyway. Sometimes we go into higher space, but 4 dimensions is the real world of real physics. So the number 4 comes in twice. Once because there are 4 fields, 4 forces, once there are 4 dimensions. And I think I want you to think of that as one lot of 4 is going across the magic square and the other one is going down the magic square. So going across the magic square you see the different fields. Going down the magic square you see increases in dimension. And this is a rough sketch, and it's not quite as straightforward as that because there are links between all the different parts of the diagram. Roughly speaking, like this. So the top row you can think of as quantum mechanics. And here you would have, from the point of view of geometry, you would use, classical geometry, you would use representation theory of Lie groups. These are very much used in quantum mechanics. And then if you go to 2 dimensions, I mean, from this point of view, 2-dimensional quantum field theory is one space, one time. And the particular class of theories I want to call conformally invariant theories, which depends on the complex structure of Riemann surfaces, this is a very well-developed branch of quantum field theory. Beyond quantum mechanics, so to speak, is time and no space. No space is finite. But the first step in quantum field theory is to go from here to there. And the theory of Riemann surfaces plays a very important role, and beautiful theory has been developed. And this is almost a rigorous mathematical theory, and in this theory, the role of Lie groups is replaced by the notion of loop groups. A loop group is the infinite dimensional group of mappings of a circle into an ordinary Lie group. So for every Lie group, there is a loop group corresponding to it, the theory of these are very parallel, and they're very beautiful results. All this has been very well worked out by physicists over the last 20, 30 years. Now, to get down to levels 3 and 4 is more serious. I focused on this block here. This one is a theory here which is very similar to the theory of Riemann surfaces in dimension 2, and it is a theory not of complex two-dimensional surfaces you might think. It's a theory of real four-dimensional manifolds which are what are called self-dual. In 4 dimensions, if you have a Riemannian metric, then you have a curvature tensor and it has many component parts. In particular, it has a part which is called the conformally invariant part of the Riemann curvature. It's called the Weil tensor. This Weil tensor breaks up into 2 parts, so-called self-dual and anti-self-dual. So if you have a conformal manifold in dimension 4, it may have one half of the Weil tensor vanishing and the other half not vanishing. Those are called self-dual. These manifolds, and the difference in self-dual and anti-self-dual is very much like the difference between holomorphic and anti-holomorphic on Riemann surfaces. And this theory is a theory which is very well suited, beautifully suited to Penrose's twistor theory. You can study this theory by going to a 3-dimensional complex manifold called the twistor space and using complex variable theory in 3 dimensions to get beautiful results about this 4-dimensional story. This theory is very deep. It includes things like work of Donaldson on 4-dimensional manifolds, but you can do many things parallel to what you can do here. So at the moment, this is something which is very much under investigation. I'm looking at it. The physicists are looking at it. There's a lot of work going on in this area. And so we've made a step from this to there. I have some ideas about this, which I won't explain. And then the last step would be to go down to the 4, where you should get down to things of dimension 8. See, this was dimension 1, 2, 4, 8. The dimensions go geometrically, not additively. Not 1, 2, 3, 4, but 1, 2, 4, 8. In 8 dimensions, there's a special geometry. If you have a Riemannian manifold of any dimension, then in general its curvature tensor has no special properties. But there are some kind of geometry where the curvature tensor has a special property. Those are called special holonomies. For example, these self-dual ones, if you have what are called self-dual Kähler manifolds, they're a special class where the holonomic group is SU2. You can have complex manifolds with holonomic SUN. You can have various groups, but there is a special class in dimension 8 related to the octonions, which are called the manifold with spin 7 holonomy. It's the last of the exceptional list of holonomies. They're classified, and there exists one. There's one in dimension 7 related to exceptional group G2, and there's one in dimension 8 related to spin 7. This is all closely related to the geometry, to the algebra or the geometry of the octonions. And this manifold, this particular kind of geometry, these dimensions, is the one which one would naturally look at if one's following the proposal I made. The octonions should be studied in detailed geometrical form. And this should be the part where you begin to hit the hard part of Einstein's theory. So when you get down to here, this is the bottom row, you see, this is where it's supposed to be the exceptional groups. Here they are in the form of geometry. This is somewhere where we would expect Einstein's gravity to be really visible. And this geometry is theoretically known. A little bit of work has been done on it, but it's still very much unknown territory. There's a lot of work here to be done for the younger generation. If you're a young geometer and you want to know where the future lies, I would recommend you to look at some of the work here. It's a very beautiful subject, but very little has been done. Very little is known. Even in the 7-dimensional case, not much is known. So this is a new field of geometry which has remarkable properties. Some work's been done on it, and it looks very promising for the future. And my hunch is that this is a key part of understanding what we need to do quantum gravity. But that's my hunch. 50 years time, some of you old people are back. You'll say, I heard, Atiyah talk about that. He was right after all. Well, maybe you are right, maybe wrong. Who knows? We can't predict the future. But, if you have to make predictions about the future, they should be beautiful predictions. If you make an ugly prediction, nobody's going to like it. If you make a beautiful prediction, it's right. They will say, here was an inspired poet. So, I like to make beautiful predictions because I believe that if God created the universe, He did it in a beautiful way. Why would He make the universe based on basic equations? All this beautiful mathematics around. Surely God knew the mathematics first. He knew about the exceptional groups, and He wasn't going to use some stupid group, uninteresting group, when He could have a beautiful group instead. So God chose the beautiful things in mathematics because they were there, and He wanted to make a beautiful universe. Everybody has to believe that, whether you're an ordinary believing Christian or a Muslim or a mathematician. Believing that the universe is built on beautiful mathematics seems to be the best thing you can make. You should believe that. If you're wrong, well, it's unfortunate. God made a mistake somewhere in His Psalms. He didn't get it right. But as long as he did his homework right, He made a beautiful universe. And we may take a long time to get there. It may not be, in our lifetime. All we can do now is to point in the right direction. And I've been pointing in these directions because I've had some thoughts about these things. I see what the physicists do. The physicists are doing very clever things, but they tend to be going round and round in circles. They're not quite sure what the final picture is going to be. I can try to describe that in the following way. There are, well, maybe I'll come to that in a moment. I'll say a word about Alan Kohn. Alan Kohn, as I mentioned before, had a very beautiful theory of non-commutative algebra, non-commutative geometry rather. He takes algebras and he applies geometrical notions to them like space and curvature, bundle. And using this model, he has even produced his approach to the standard model of physics. And he takes a situation where the space-time is not just one copy of space-time, but two copies of space-time very closely, very little distance apart. And on this model, he builds his machinery, he gets something like the standard model, which is quite a remarkable achievement. And in arithmetic, he ends up with some approach to the Riemann hypothesis, which is where the number theory came in. I've mentioned here the famous relation between algebraic geometry over finite fields and the Riemann hypothesis over finite fields, which was conjectured by André Weil and proved by Deligne and Grothendieck many years ago. Now, in Kohn's theory, his non-commutative geometry is based on a homology theory, which he calls cyclic homology, and is developed for associative algebras. See, if your ordinary geometry is functions in a space are commutative, and ordinary topology uses ordinary homology theory and so on. But if you're dealing with non-commutative geometry, your only thing you have associativity still, then the associative law has an important property, and for example, if you think about matrices, the important property of matrices is that if you take three matrices, A, B, and C, and you multiply them together and take the trace, that's the same thing as multiplying them in a cyclic order, CAB, and taking the trace. You usually see that. So cyclic homology is based on the notion of traces of triples of matrices, and it leads to his geometry. Now, Kohn's theory only deals with associative algebras, so he can't deal with the octonions. So that's why I think he's not quite finished. I mean, his theory is very beautiful, but it doesn't totally convince the physicists. The way he gets into geometry relativity is rather ad hoc. He gets a standard model, perhaps convincingly, but it doesn't get to the real heart of gravity. And I think the reason is that his theory deals with associative algebras only. And as Dirac thought associative algebras were the beautiful things, but both of them missed out the next one. So that's my view. Now, when I'm talking about Alan Kohn, let me make one other comment. Alan Kohn's theory is very algebraic. It's based on algebra and also based on the spectral properties of operators. And he links it to the physics where you look at the spectral lines of atoms and so on. Very much like Heisenberg did when he got into matrix mechanics. And I think the difference between my philosophy and Kohn's philosophy is like the difference between the philosophy of Heisenberg and the philosophy of Schrödinger and Dirac. Heisenberg developed algebra, commutation relations. Kohn is very much in the spirit of Heisenberg, whereas Schrödinger wrote down a differential equation, and Dirac wrote down an even better equation. And this equation later on was shown to be equivalent to Heisenberg's formulation, but from a different point of view. So I belong to the Schrödinger-Dirac school, and Kohn belongs to the Heisenberg school. We may be more or less equivalent for many purposes, but for the purposes of gravity, I think Heisenberg doesn't win. I mean, there's something missing here, as yet. That was a philosophical remark. Now, let me go back. I didn't talk about number theory in here. You maybe think I cheated in the title. So let me just end up here. See, Hilbert's dream was always that the Riemann hypothesis, which is about the zeros of the Riemann zeta function, the non-trivial zeros, they're supposed to lie on a line. And the idea was if you could find a natural operator whose eigenvalues would be these self-adjoint operator, whose eigenvalues would be these zeros, then of course, because it's a self-adjoint operator, they would lie on a line. So the idea was, can you find such an operator? And where would you naturally look? You would naturally look in physics. So the idea was, Hilbert's dream was, if you can find a natural physical interpretation of the operator whose spectrum gives you the zeros of the Riemann zeta function, then you'll have proved the Riemann hypothesis. Well, this is the dream. It's still a dream. Alan Kohn has tried to get the Riemann hypothesis out of his framework. He hasn't quite succeeded. And I was speculating that Kohn has not succeeded because he hasn't really touched gravity properly, because we're dealing with associative algebras. So if I want to be really brave, make a big conjecture, I want to suggest the Riemann hypothesis should come out of quantum gravity. It should somehow correspond to the Hamiltonian of quantum gravity, if we know what that means. We don't know quantum gravity yet. Its theory does not yet exist. If we do have the theory, then we may be able to answer the question, what is the Hamiltonian of the theory? And that would be a very fundamental operator, and because it's so fundamental, it will obviously have to be self-adjoint, and it's so fundamental, it might be related to number theory. So you close the circle and you achieve Hilbert's dream. Well, that's my, I don't put very much, I'm not waging a large bet on that, a small bet. Some of the other things I think I believe more. But philosophically, it has the right idea that if there is going to be a solution of this difficult problem of Riemann hypothesis, many people have tried it for hundreds of years, then you need to have a really powerful new idea. The idea of finding an operator whose spectrum gives you the zeros is not new. But the question is, where would you find it? What should it represent? It should represent something new in physics. And so it might be related to the ideas of quantum gravity. Well, now, let me end with Dirac again, because I like Dirac's quotations. So, this is about number theory. At the end of his talk, he looked into the future. He said, there is thus a possibility that the ancient dream of philosophers to connect all nature with the properties of whole numbers will someday be realized. To do so, physics will have to develop a long way to establish the details of how the correspondence is to be made. One hint for this development seems pretty obvious, namely the study of whole numbers in modern mathematics is inextricably bound up with the theory of functions of a complex variable, which theory we have already seen has a good chance of forming the basis of the physics of the future. The working out of this idea would lead to a connection between atomic theory and cosmology. That's a brave prediction, you see. He wants to incorporate integers into physics. He wants to link atomic theory with cosmology, and I've been trying to copy him in some of the things I've been saying. So I believe I'm following a well-trodden path. Dirac said all these things 80 years ago. It takes a long time for these ideas to be achieved, but we have to have these, and we have to have dreams. So let me finish by quoting a poem by a not so well-known poet, namely myself. It's the only poem I've ever written. It wasn't meant to be a poem, but it became a poem. I was asked to contribute a few lines to the IHES outside Paris when they were celebrating some anniversary, and so I wrote down something which came out, and here it is for you. And I called it Dreams. It says, in the broad light of day, mathematicians check their equations and their proofs, leaving no stone unturned in their search for rigor. But at night, under the full moon, they dream. They float among the stars and wonder at the miracle of the heavens. They are inspired. Without dreams, there is no art, no mathematics, no life. Thank you.